So just be aware of that. All right, so we started our recording now. So welcome everyone to this episode of Map Time Davis. My name is Michelle Tobias. I am the Geospatial Data Specialist at UC Davis Data Lab. Today we're going to be having a presentation from Andy Lyons on working with Cal Adapt climate data in R. And I think this is going to be a really awesome workshop. A little bit about what map time is in case any of you are new to map time or coming back after a while. Map time is literally time for making maps. We get together as a meetup and we share skills about map making. And this is a concept that happens all over the world at this point. Map times are meetups that happen in most major cities. At least at some point there has been, I feel like. And our flavor of map time, because we're on a university campus and sponsored by a university entity with Data Lab, we tend to be a little bit more on the research side of things. We tend to do a little bit more workflows with research data and things like that. But every map time kind of has their own special flavor that's, it's tailored to the folks that come to their particular map time. And then I also mentioned Data Lab, that's where I work. We are an entity on campus. We're housed within the UC Davis library, physically and metaphorically, and we help folks with data needs. So we help people with the entire pipeline of working with data from planning, data gathering to how to process it, how to clean it, how to do processes on it like machine learning, or in this case with map time, I focus on a lot of spatial data processing and how to analyze spatial data. So we cover everything pretty much from text to other types of data too. So that's a little bit about Data Lab in a nutshell. You can always visit our website and get some more information about that. I am going to paste a couple links into the chat for you. We've got a couple really good workshops coming up this quarter. If I can find my chat window, that will help. So you can feel free to check out our upcoming schedule. We've got all kinds of good stuff, including SQL and Earth Engine and participatory mapping kind of things. And you can find all of that on our schedule, and also they're all on the Data Lab events calendar too, so you can take a look at what's going on. There's also a lot of other events in Data Lab that might be of interest. The last link that I pasted in the chat is for our Map Time Davis Council application. We are looking for folks who are interested in helping us produce map time. It's a thing that can only happen because of community involvement. And so if you have an interest in helping find workshop presenters, mentor workshop presenters, we need help with a lot of the administrative things. Naomi says in the chat, do it, it's fun. Yeah, both Naomi and you'll see Alex Mandel also as a helper today. And I and several other folks have been working together for the last year on Map Time Davis Council to produce this year's workshop series, and it really is fun. It's a great networking opportunity. So if you feel like you don't know how to network and you want to learn, Map Time Davis Council is a great way to do that. You get to meet a lot of people, and you get to learn new skills too. So we would love to have you. Please fill out the application form, and if you have any questions, you can always contact me or anyone on Map Time Davis Council currently, and we will be happy to answer them. So that's my plug for things that are coming up and fun things that are happening in the world of Map Time Davis. So I hope you'll join us for future workshops and possibly next year on Map Time Davis Council. And with that, I think I will turn it over to Andy, our speaker today, who is going to tell us a lot more about working with climate data in R. So this is, I should also mention, this is a joint workshop with the Davis R users group too. They helped us with some advertising and things like that. So we're glad everyone is here. And so I will now pass it over to Andy.
Thank you, Michelle. And yeah, thank you to everyone who's helped organize this. For those of you coming today, I know this is a busy time of the quarter. So thank you for spending a couple of your hours learning about climate data and working in climate data in R. I'm really pleased to be here. I've been coming to Map Time Davis workshops and events since they went online. So really pleased. I've signed up for a couple of them. So it's great to be here. Yeah, and thank you to the committee and the Davis R users group. So I'll put the link right now. Okay, so thank you, Michelle, for putting a link in the chat window to the slides for our workshop today. So what we're looking at here is the kind of a menu. This is a menu for more like a 3 or 4 part workshop series. So we're not going to hit everything, and this is still very much a workshop series in development. So we'll get as far as we can. What I would like to focus on will be part 1, which is basically introducing you to working with climate data and using this R package that I'll talk about to get data directly into R through an API, which is really handy and saves you a lot of work. We'll also get through a good bit of part 2, where I'd like to introduce you to some best practices for working with climate data, because it is kind of complicated data to work with, and you have to kind of know how to use it properly, as well as just sort of the technical aspects of working with climate data. Part 3, I don't think we're going to do today. That's techniques for working with large volumes of data, basically putting them into a local database as you download them. But I do want to share part 4, which is new to today. So I've been working on developing methods and examples of working with climate data in R as rasters, as opposed to tables that you've queried. So, and then part 4 or part 5, also we're not going to get to today, but there are some shiny apps. I think these, it's grayed out here, but these links are live if you do want to practice running some shiny apps working with climate data from CalAdapt. So let me go to the first set of slides. I'd ask all the helpers, please chime in if needed. If my audio goes out or the questions that come up in the chat window, I'll kind of monitor the chat window as best I can. Okay, so I'm now at the first set of slides, and I would like to pause here for like maybe 4 or 5 minutes, because I would like everyone, if you haven't already, and I suspect most people haven't, to be able to do the exercises that we're going to do today. So I'll put these links in the chat window where Michelle has already put them there. So setting up your RStudio environment, in about 10 minutes or so, we'll be working in RStudio. I would strongly encourage everyone who has an RStudio Cloud account to go there and then click on the RStudio Cloud project link that Michelle put into the chat window and clone it. In fact, I'll do that right now, just in case you haven't used it. Even if you are not an RStudio Cloud user, I might recommend that you do this right now anyway. You can set up RStudio Cloud an account with your Google credentials, your GitHub credentials, I think. It takes about 2 minutes, and then you have a working kind of virtual RStudio environment. If you are, if you want to work on your desktop, you're welcome to here, and I'll put these links for RStudio desktop users in the chat window. But the caveat is if you're going to use RStudio desktop, fingers crossed, there's a setup script that will install the packages. So you click on there, fingers crossed that will work for you. And then there's another link to download the exercises and the data for RStudio desktop. But you're kind of on your own in terms of setup. You just don't have time to troubleshoot setup issues for RStudio desktop users. But let me click on this RStudio Cloud project. I've already got RStudio Cloud open in my browser here. And it takes a second. If you're not logged into RStudio Cloud, of course, you're going to have to do that. Basically, when I click on this project link, it's making a temporary copy of this RStudio Cloud project with all of the packages, all of the data files. We'll see them in a second here. But it's a temporary copy. So if I want to save this project in my personal RStudio Cloud workspace, then you just have to click the save a permanent copy button. All right? And then you can relax. We'll come back to this in about 10 minutes. Okay. So once again, please go ahead and click on that RStudio Cloud project link, and we'll get there in just a few minutes. The best thing about being able to do Zoom workshops is you can make these things interactive. All right. And I'm going to keep going. If anyone's having deal breaker problems with that, please let me know. But let me tell you a little bit about myself. So I work for UC. I'm with the Ag and Natural Resources Division. This is one of the lesser known parts of the UC system. Most people think of the campuses and the labs, but there's a whole other division, Ag and Natural Resources. Many of you at Davis might know about this. I'm officially employed by Davis. So this division of UC is administratively assisted by the Davis campus. We have offices all over California where we have farm advisors and other kinds of cooperative extension researchers helping growers and land managers. We've got 9 field stations. We have clusters of faculty on 3 of the campuses, Davis, Berkeley, and Riverside, and a few people at Santa Barbara and Merced. And then there's a bunch of these statewide programs, some of which you may have heard of before, like 4-H or Master Gardeners. These are public-facing statewide programs. There's a bunch of other ones focused on nutrition, integrated pest management. Anyway, I work for the Informatics and GIS program within UC A&R. We are a smallish geospatial research and innovation unit to support this whole network. So really, really like it. It's very, very applied. And if you have any questions about this kind of as a career path or interested in opportunities, I'd be happy to chat with people. I also want to thank a lot of other people who have been instrumental in making this project possible. It's the folks at the who run CalAdapt essentially, the developers and administrators there, and then also a couple of my colleagues, Shane Fire and Maggie Kelly. So CalAdapt, you may have probably have heard of it, I would think. It's been developed and heavily supported by the state of California for many years. All right. Okay, so what are we going to do today? My hope is to get you familiar with working with this R package that makes it easy to import data into CalAdapt, to get some hands-on practice very soon on actually importing data into CalAdapt, go over some best practices for wrangling it, for working with climate data, for aggregating it, and then to work with, to see some rasters, uses of rasters. I want to get, by the end of, by noon, by lunchtime today, my hope is that you will have some working code recipes. We're going to do some notebooks. You can save those notebooks. It saves it as a nicely formatted HTML file that you can then keep. So when you want to come back and do this stuff at some point, they're there for you. And I'm also happy to share a ebook that I have been working on. It's still very much in progress, but it's basically, it's a bunch of code recipes for working with climate data in R. So I'll make some references to that as we go along as well. But if you're a power user or this intrigues you or might be helpful, feel free to go to that ebook. Also looking for collaborators. You know, if you're working with climate data, CalAdapt or otherwise, I've discovered, you know, it's a lot of reinventing the wheel. So my hope is to get collaborators to develop code recipes for working with climate data. Okay, so a little bit about CalAdapt. So it is a data portal and a website. Most people are familiar with the website, where there's lots of these ready-made charts and maps that you can get. It is an official data source for the state of California, and it is peer-reviewed climate data. So the CalAdapt team, they don't generate any of these data. These are all peer-reviewed data from climate scientists. All of it has been vetted by state agencies under the 4th climate change assessment, and they're currently getting the data ready to go from the 5th climate change assessment, which is coming out, which should be out by the end of this year. Here are some examples of the type of data that you can get on climate data. There's a lot of modeled climate data. So this is the data that's coming out of these big climate models. Of course, it's the usual suspects, your daily temperature, precipitation, snow water equivalent, and so on and so forth. But then there's also a bunch of derived layers, these are mostly raster layers, on things like wildfire risk and that, you know, evapotranspiration and so forth. Right? So there's a lot of modeled climate data, both the primary data that comes out of the climate models and some derived variables. A little known fact is that there's also a fair bit of observed historical climate data that's been interpolated. So the Livni data set is one, and then GridMet is a recent addition. Right? So These are two out of, the PRISM is another one, but these are two out of maybe the three kind of go-to data sets for historical observed data, which is mostly interpolated from weather stations. But if you know, so even if you're not interested in the future or working with model data, it could be a good resource for you. This little diagram here is showing the extent of the, at least for the modeled climate data. I'm not sure if the GridMet covers all of this area, but it's all of California, all of Nevada, and bits of the neighboring states. And it's all been downscaled to about 6 kilometers, which is pretty good. Here's a link here to there's more descriptions of the data sets on CalAdapt on their website. So if you're new to climate data, you might be wondering, well, like, where does this stuff come from? So it starts with carbon emissions. So we're always hearing about carbon, you know, in the atmosphere, and that is a big question about the future, and that is a big impact on how atmosphere is going to change and how weather is going to change in the coming decades. So those scenarios, they're called emission scenarios. There's 2 of them that we'll be working with for the future. There's also a historical emission scenario. Those are called RCPs, representative concentration pathways. That's what that stands for. So those are fed into these big supercomputer level global climate models. There's 32 of them that are out there. 10 of them have been endorsed by California. 4 of those are turned on by default because they're called priority models. They represent the full spectrum of climate futures for the state of California as it was vetted by climate scientists a few years ago. And what those things spit out are going to be global rasters of things like temperature and precipitation. The big pixels, right? Because the Earth is big, and we're still developing computing power. So those models are run both hindcast as well as forecast. So like going back from 1950 up to 2100 for the CMIP5 data. So now we have all of these global scale, large pixel raster layers of future and past modeled precipitation and temperature. Those then get fed into a downscaling algorithm called LOCA. And that's a statistical downscaling method. And it basically takes those 100 kilometer pixels and shrinks them down to 6 kilometer pixels, approximately. And then but it's still like temperature and precipitation, your kind of core atmospheric variables. And then those can get fed into other models which generate these derived variables, such as snowpack and humidity and so forth. Okay, so in a nutshell, that's kind of the work pipeline for where the climate data that we're going to work with are coming from. So you might wonder, well, how do I get to these data? So at least with the CalAdapt, it all starts from that 4th climate change assessment and other peer-reviewed studies. They've got the data up on servers. There is an FTP server. So if you're really interested in the source science data, you can get it all by FTP. It's in that CDF format. But they also have this API where they've crunched TIFFs and other kind of variables, and that's where that's what we're going to work with. And those APIs are designed for user applications. So in the last year and a half or so, myself and my colleague, we've developed programming bridges to make it easier to work with the data via the API in software environments like R and Python. So that's kind of the piece that we're going to be working with today. There is a Python library that you can use as well that my colleague Shane Fires put together, and that includes Toolbox or JS Pro. So if you're primarily interested in working in the Esri environment, that's another way you can get to the data without having to like download ginormous TIFFs and do all this wrangling. Okay, so here's some, I won't talk through every bit here, but the point here is there are different ways that you can get to the climate data from CalAdapt. The website does have a nice little download tool, so that's a good option. You can pick the data set and your area of interest. There's that FTP server, and then, but there's also the API allows you to query like specific locations, because you probably don't want to know, the future of the whole West Coast, maybe just a handful of your, of locations. That's called querying, and that's what we're going to look at today, mostly with the CalAdapt R package. Okay, keep on going here. So why might you want to do with this? So climate data is big data. It's a little bit like drinking out of a fire hose. So it's challenging to work with. So that's one reason that, bringing it into R gives you some options to filter it and to just keep what you need for whatever your use case is, whether that's research or maybe a decision support tool, but also converting these climate variables like temperature into more actionable information, right? So that takes some data chugging. We can get out of the climate models, we can see what the rolling average of temperature is going to look like at the end of the century. But that's not very useful to most people. Most people are interested in, like, how is this going to affect my crops? How is this going to affect my water infrastructure? How is this going to affect human health in my city, right? So to translate that, you need to do some data manipulations. R is really good at visualizations, so it gives you some options there. Oftentimes, you need to integrate the climate data with other data, right? Such as census information. Maybe you're doing something with biodiversity or habitat niche models, maybe some economic model, so on and so forth. R has tons of packages out there that you can use, some of them which are specific to modeling climate data, like chill portions or chill hours. You can make your own custom models and decision support tools. This little thumbnail image takes you to a Shiny app that's relatively recent and is predicting when pistachio nuts are going to mature, essentially based on weather. Okay, then pause for a breath there. I don't see any questions. Okay, we'll keep going. I'm going to get to the notebooks very quickly. So CalAdapt R is a R package. This is a classic API client. It does one thing and one thing only, and that's getting data from CalAdapt into the R environment. Then its job is done. So that's a small but pretty important and not trivial task. But once it's in R, then you can use all your other go-to data science packages, like the tidyverse. Stars is the one we're going to look at for handling raster data, and so on and so forth. Okay, so the role of R is, CalAdapt R is really just to get the data into R. It's fresh out of the oven, so it's relatively modern in terms of using, the current standard data classes for spatial data and tabular data. It's pipe friendly, as we're going to see. And yeah, so you can use this R package to query the CalAdapt data sets with your own points or polygons. There's also about a dozen of these preset areas of interest. So just pass it the name of a county and it'll send you back the data for that county, or watersheds or census tracts and so forth. And you can get the data back either as tables or data frames or as rasters. We'll see both of those today. So it really facilitates working with climate data in R, but you still know how to work with R. You need to know what climate data you're looking for, which is often the million-dollar question. And you need to know how to use climate data properly, right? Because you are getting under the hood, and it's easy not to, you need to know what these data represent to use them properly. Okay, the go-to place to learn about this R package is the website. I won't stick it in the chat note right now, but it's right there. There's lots of tutorials. All of these workshops, I'm linking them there. There's this code recipe book I was just referencing to, a couple presentations and so forth, as well as five vignettes, which are kind of like tutorials. Okay, here is the basic workflow for getting data through this package. You need to know your location of interest, right? That's kind of standard. Then you can, once you know that, plus what data set you want, this is the technical workflow. You need to know what data set you want, what is location, what time period. All of that is part of an API request object that you construct by stringing together some functions. Then you feed that API request object into another function that actually communicates with the server and brings down the data. At that point, you're kind of done with this R package, and you start working with those results in, to get them in shape for whatever you're going to do next, whether that's some kind of statistical model, or maybe a report of some sort, or just a visualization. And yeah, so that's essentially the steps to working with the data. Here's what an API request object looks like. This is where it all starts. So basically, as you can see here in this little sample code, it's a set of functions that are strung together with pipes. And each one of these functions provides a piece of information about the data that you want, such as what is the climate variable, such as what are the emission scenario, and so forth. We're going to work through this in a second, but that's what it kind of looks like. So the pieces that you need to put in that string of equations are going to be the location of interest. You have 3 choices there, depending on how you want to specify your location of interest. You have to specify the data set that you want. And again, there's a few options there. If you're interested in some of the modeled data, you can string together these 4 functions, include those in your request object. If you're interested in the observed LibMe data, you can throw in these 3 functions, string them together with the correct arguments, and get back and specify one of the LibMe data sets, the interpolated observed. Or if those are all convenience functions. You can also specify the slug, which is kind of like a primary key, or like a ID value for each and every one of the over 900 raster series that you can get through the API. Each one of them has a unique slug. So that's another way that you can specify the data that you want. You need to specify your date range. And then if you're querying by polygon, then you need to specify how you want the pixels within that polygon to be aggregated. So you get one value back for that. Okay, so here's a quick example, and then I think we'll go to the notebook. So here you can see we're loading up the package. This is a API request that we're putting together. I think this is for the San Diego Zoo. So we're passing it a location by giving it longitude and latitude coordinates. So we're using the function that does that. The next function in our definition here are the climate variables. TASMAX and TASMIN stands for the daily maximum and minimum temperatures. We're asking it to give us back the data for 4 of the 10 global climate models, the first 4 of those priority ones. We're asking it to give us the data back for each of those GCMs under 2 emission scenarios. And again, those are the 2 future emission scenarios. We're asking it to aggregate the data by year. So we don't have to do that on our own. The server will do that for us. And then finally, we're specifying the time period. In this case, we're specifying start and end dates by year. Right, so that's a fully baked API request object. If you just run it by itself, it'll spit out what's in there. Right? So that's one way you can check your API request object. There's also a function called pre-flight, which will check that your API request object is error-free. So we run that. You can plot an API request object, and it will show it up there. My leaflet map is, hold on. Yeah, leaflet maps in Markdown don't always work well. But that little leaflet map will show you the location in your API request object. And finally, we're ready to fetch some data. So we take that API request object and we feed it into a function that actually talks to the server and brings down data. And what do you get? You save that as a data frame, and you get a data frame, right? It's a well-structured data frame. The number of columns will vary a little bit, but the first one is always going to be the ID value of the location. So in case you need to join this back to location data, maybe it's a census tract, and you want to join it back to the census attributes of a census tract. That's the first column. Other columns tell you about what the different properties are. And then the last column is going to be your climate value, in this case, temperature, because we have to get temperature. So basically each row here represents one temperature for one date, for one GCM, and for one scenario, for one location, right? So you can get lots of data down. Okay, so I'm going to talk quickly through this so we can get to the notebook. But basically, if you do want to specify your location of interest using one of these areas of interest, you don't need to pass it a polygon. You just specify what is the preset area of interest type or layer that you want and which specific one that you want, and you can get it. We'll come back to this if we need to, but it makes it an easy way to get data. If you do have your own area of interest and you have a simple feature data frame for it, polygon layer or point layer for it, you can pass that as well. Okay, so, but let's go to RStudio and we're going to open up a notebook. If you haven't worked with notebooks before, not everybody has. It's a form of R Markdown. I don't use them on a day-to-day basis, but I do like them for workshops, like all Markdown documents. I'll come to your question here in a second, Naomi. Like all R Markdown documents, there's, you've got your header, the YAML character formatting with things like that little hash sign that'll be rendered as a heading level. The actual code that you're running in, the actual R code, you put in these little gray boxes, which are called code chunks. And it's just a plain text file. So you can, you just type in the backticks and then R in curly brackets to create a code chunk. If you do want to run just the line where your cursor is, you can click that run button. You can also just click in here and hit Control Enter. To run the entire code chunk, you can run Control Shift Enter. By default, the output of code chunks will appear underneath the code chunk within the notebook. If you prefer your output to appear in the console or down in the plot window, as it normally does, you can change that with that little button up there. And there's another little green button that you can run to run all of the lines in the code chunk. And so I think if you haven't used them before, I think you will like them. You can run all code chunks above the current one. There's another button. Okay. One of the cool things about our notebooks is that every time you can save, it generates a HTML file in the background. You don't have to do anything extra. And when you're all is said and done, you have a nice HTML file that you can save and keep. Comment, it's a little glitchy or can be a little glitchy. I've seen this error message quite a bit. So if you see a little yellow bar in RStudio with a little error message, odds are you can just ignore that. It just means it's having trouble saving or rendering the R Markdown notebook as HTML. And so just close that up. When you're ready to save it for good, if you clear your knitter cache, that will almost always get rid of those error problems. So that's just an FYI. Okay, so let's go to our first notebook. So go ahead, and if you haven't already, fire up RStudio and open the project that we were looking at. And how about people, once you've opened up RStudio Cloud, I'm going to assume people are using RStudio Cloud. I hope that our users can figure this out on their own. Go into the Notebooks folder and click on Notebook 1, Getting Started. And then give me a thumbs up or a stop sign if that's problematic. Project. I can see a few thumbs up here. Hopefully I'm the only one having. Okay. Okay. Okay, let's keep going. All right, so I'm going to talk through this. You may or may not be able to view my screen share, but I'll talk through. So assuming that you're in Notebook 1 getting started, I'm going to just come down to code chunk number 1. So scroll down to code chunk number 1 I'm going to run all of these lines by hitting Control-Shift-Enter. So I click in the code chunk. I'm going to hit Control-Shift-Enter. And it's going to basically load these various libraries into memory. Okay, so fingers crossed that worked. Now I'm going to come down to code chunk number 2. This is also setup stuff. So go ahead and run code chunk number 2. This is where we're specifying our preferences for some function that may be in multiple packages. So filter, count, and select are notorious for this. These are generic function names that are in many R packages. And basically here we're saying, if it finds one of these, look in the dplyr package, because we use those packages for data munging. Okay, so now we're down to part 1 of our notebook. So we're basically going to create this little graph that you should see, this little thumbnail sample. So we're going to get some data for daily temperature, and we're going to plot it. So that's where we're working towards. Go to code chunk number 3 and run it. Code chunk number 3, we are creating an API request object. This should look familiar. We're specifying a point location. We're telling it to use the 4 GCMs. The first 4, I'll talk about those constants here in a second. 2 emission scenarios, RCP 4.5 and 8.5. RCP 4.5 is kind of the medium emission scenario where at the global scale, carbon emissions or greenhouse gas emissions peak around 2040 and then start to gradually decline. RCP 8.5 is a less optimistic emission scenario where carbon emissions at the global scale continue to increase for the entire century. So we're going to get an update, I think, on those in the next climate change assessments. I think they're still going up. Okay, and so on and so forth. So we're specifying it. We wanted to get them by year for 50 years, mid-century. And Tasman and Tasmax are the climate variables. Again, daily maximum temperature, daily minimum temperature, and these are going to be averaged per year. Okay, there's a pro tip there saying building those constructor functions or those API requests, the order doesn't matter as long as all the pieces are there. Code chunk number 4, go ahead and type in, code chunk number 4 is inviting you to look at some of the constants that are built into the package and help you construct your API request. So if you just type in GCMs and hit run there. So GCMs is a constant that comes with the CalAdapt R package, and it has the acronyms for the global climate models that are available through CalAdapt. They have funny acronyms. I've never even tried to memorize these. You'll notice there are also some 32, there's some ensemble GCMs as well. So basically those are ensemble models of all of the 32 global climate models that have been developed and recognized under the 4th climate change assessment. Okay, so let's keep going here. I'm not going to read through every detail just for time, but you're welcome to ask questions or come back to some of the stuff. Code chunk number 5, go ahead and run that. We're basically looking at what is inside this API request object. It just spits it back out. Code chunk number 6 is the same thing, but it's basically there we are just showing you there's a convenience function to change the colors that are used when you get messages back. So if you're, you can change the word dark to the word light. If your RStudio has a light colored background. Okay, that's just bells and whistles. Let's go to code chunk number 7. Run down code chunk number 7. This is that pre-flight function I was telling you about. It's basically checking your API request for some common errors. Is the location within the boundaries of the, that covered by the data? Are the dates valid? And so on. Did you forget anything? Right? So this one looks good. Go ahead and run code chunk number 8. Come on down there. So here we're plotting it. And hopefully that would work for everybody. So it throws up a little interactive leaflet map showing the location in your API request. Code chunk number 9, doing the same thing, but in addition, it's overlaying the actual grid cells of the climate data. So again, those are roughly 6 kilometers. They're 1/16 of a degree, so that's roughly 6 kilometers. And it's, if you're querying a single point location, obviously it's just going to be in a single grid cell. But sometimes you're querying a polygon. You might want to know, am I getting back 10 or 100? How much is it getting covered? Okay, let's go down to code chunk number 10. Code chunk number 10, we're actually going to fetch some data. You can change quiet equals to true. You could change that to quiet equals to false if you want to see a little progress bar. But this is where it's actually communicating with the CalAdapt server and bringing down the data. And what do you get back? If you look at line 154, we can see the first few rows of that tibble that we got back. Okay, so if that worked, you have successfully gotten some data, climate data, via the API. So one thing, the units, one of the nice things about CalAdapt API in this package is that it tells you what units you're getting down. So you can see if you look at the val column, it's the last column of the data frame that you got back when you queried the server, the units are K or Kelvin. So that's not very intuitive for most people. So in code chunk number 11, go ahead and run code chunk number 11. We're doing two things here, right? So this is now a dplyr syntax. This is straight up dplyr. We are filtering only one of the emission scenarios. So you might remember we got a whole bunch of, we got temperature values for 2 emission scenarios and 4 GCMs. So that's 8 times the number of years. So here we're using the filter function from dplyr and say, we only want to keep the values from RCP 4.5 and just the TASMAX, because again, we're coming to make a ggplot line series. So we only want to show a single RCP because obviously the time series for the different RCPs are going to be real different, right? Because there are different emission scenarios. The time series for the different GCMs will vary a bit, but they certainly won't vary as much as between emission scenarios. But the other thing that we're seeing here in code chunk number 11 is we're using the mutate function to create a new column in this tibble where we're converting the units from Kelvin to degrees Fahrenheit. And this is possible because the column type is the units. It's coming from the units package. Right? So now you can see a new column after you've run code chunk number 11 for the maximum daily temperature averaged by year in Fahrenheit. So now we're pretty much set to do a little plot. So go ahead and run code chunk number 12. This is a ggplot command, very popular plotting packages. I won't try to talk through ggplot syntax. You can probably, if you've used this at all, you can probably follow it. Yeah, but basically we have plotted each of the time series as a separate color using ggplot, and we're telling it to use the temperature values. Okay, any questions? Okay, we're going to skip challenge number 2. That's basically, there is a little hint there, or a little answer key. It's basically asking you to repeat what we just did, but using the higher emission scenario. And let's go ahead and we'll skip challenge number 3. What is this one doing? Oh, that's basically the same thing, except instead of the maximum daily temperature, instead of the minimum daily temperature, it's asking you to create the same kind of plot for maximum daily. So that's, again, a different climate variable plot. Okay, let me quickly address Naomi's question, and then we're going to take a break. So Naomi was asking, using a preset geometry, is there a list of valid names to select from? Yes, so there are some constants in the R package that will help you identify one of those preset areas of interest. So if you, I'm just going to type it here in chunk 14. One of them is called, let's see, it's called ID. No, it's going to be CA. Can't remember. Nope, not that one. AOI. Yes, okay, so AOI preset underscore types. So if you type into R, AOI underscore types and run that, those are the names of those preset area of interest layers. So you've got that, and then in addition to that, you're going to have to say each one of these is a field. If you want to see what these look like, there's another function you can run called CA AOI preset geom, and then in there you type in one of those names, such as the name counties, and save that to a variable. I'll put this in the I'll put these two lines in the code. If you want to take a break, feel free to go ahead and start your break. I'll just talk for a couple more minutes. So basically, all of these area of interest presets are available as simple featured data frames, and you can grab them using this function called CA underscore AOI preset underscore geom. And then you pass it the name of one of the preset layers. And so then you can look at the attribute table to see what columns are in there. And there's another field that you can, there's another constant called AOI preset ID fields. And then that's a list. So you type $, and then the name of one of the layers. You run that, and then you see the names of the fields that you can use to specify your feature or features of interest. And then the last thing you need to do is find your FIPS code or your ID code or the name of your Route 10 or whatever the case may be. There's examples of that on, there's a big net that gives you examples of creating that. Okay, so let's take a 5-minute break, and then we shall proceed. If I went too fast or people have questions, I'll hang out for 5 minutes and answer questions. Otherwise, see you back in 5 minutes. All right, before we resume, pause. Any questions or comments or? All right. Yeah, Aviv.
Yeah, hi, thanks. So this was really great, the website about the AOI presets and identifying counties. And I see that you can identify the counties by the numerical value, so like 06001 or something like that. But how do you query the numerical code value if you know like the name of the county? So like Yolo County, Sonoma County, things like that.
Very good question. Yeah. So here's a quick way I would do it. So you can use, let's say you're interested in counties, right? So I can type CA AOI preset geom and then counties. So that's going to return a simple featured data frame, getting it online. Now pipe that into ST drop geometry. So what that's going to do, it's going to like throw out that geometry column and just give you like a plain data frame. And then pipe that into view, capital V, and run that. And then what that's going to do in RStudio, it'll open up the attribute table essentially in the viewer pane. And then here you can kind of eyeball like a FIPS code. So county, like many of them, the census tracts, there's a FIPS code. Unfortunately, we can't use the name of the county as a unique identifier because there's some counties in Nevada that have the same names as counties in California. So,
Okay.
so unfortunately, name is not a unique field. So we have to go to FIPS code or ID. I think ID is one that the CalAdapt people put in. But it's usually gonna be like FIPS code or the Hux10 code, since tracked ID code. Some of them are names. But yes, that's essentially how you can find the value of the feature you're looking for. That's one way
Great.
to do it.
Thank you. That was very helpful.
Yeah, there's lots of little tricks like that. Okay, let's keep going then. Oh, okay, let's see if I missed any. Okay, we got through that one. That one. Okay, and I'm going to keep going. Okay, next, let's go back. So I should have highlighted here on the menu for today's workshop. There are links to those same notebooks that are rendered as HTML, including the ones with the solutions. So even if they're not working for you, or you just don't have the patience to open them up, you can click on these links and see working R code from those notebooks. Okay, let's go to part 2, because this is kind of important. It's not. We can do all kinds of data science and visualizations and statistics on climate data, but like any kind of science, you need to know what the data represent and how to work with them. All right, so let's talk a little bit more about data, climate data specifically. So you might be wondering, how can I find, like, there's lots and lots of climate data in CalAdapt API and other portals. With CalAdapt the CalAdapt specifically, there's a copy of this catalog. So I just said there's like 935 raster layers that you can get via the API. And there's a copy of the catalog. It's essentially a data frame that has information that can help you see what's available, what it represents, and like how to specify it. So of course you can troll through the CalAdapt website. They do have pages on that. Sometimes it's hard to find. So anyway, so there is a function called ca_catalog_rs. And if you run that, it returns a data frame. And if you run that, you can see the columns in this catalog. I'm calling it a catalog. It's really just like it's a glorified CSV file. Anyway, there's a name column, which tells you mostly what it comes. There's the slug column, right? So that's kind of the unique identifier. If all else fails, you can specify a data set by its slug. That will always work. There's the URL. These URLs are not that helpful. They'll take you to an API page. It's not like a page that's going to describe, like how did they compute base flow, for example. But then you see the date range that is available through this specific layer, and some other information about it. Okay, so if you do want to check out the catalog, I'll just throw this little thing in the chat window here. A good way to view it. Oops, sorry, I haven't said it to everybody. If you do want to just browse the catalog, I find that opening it up in the viewer pane in RStudio is good, because then you can use those little filter buttons in the viewer pane. Like if you're looking for the word snow, or you're looking for the word like evapotranspiration, you can turn on those little filter buttons and then see what you find. There's another function that you can use called CA catalog search. That's a function from the package, and you can put in a keyword there, and it will return a data frame with those variables. So we can see here the word snow. There's actually 94 layers that have the word snow, either in the name of it or in the slug, right? So I can recognize some of these. We've got the Livni data, which is snowfall, and so on and so forth. But there's a lot of them. Livni is observed. So this is going to be an interpolated snow layer, that first one. And then there's also modeled snowfall, right? So we can see that one too. Yeah, and sometimes you just want to see, like, what data set you want to work with. Maybe the slug. If you feed that into your that CA catalog search function, it'll show you the properties for just that layer. This is helpful because sometimes the units that you get back are not necessarily clear. So like this snowfall layer, the units are millimeters per day. If you're just looking at the numbers, it may not be clear, what are the units of those numbers. Some of them are really weird, like precipitation is like kilograms per second per meter squared. It's some weird precipitation unit. Okay, so that's a little bit about how to find data. Of course, you control through the CalAdapt website. Let's talk about how to use climate data wisely. So here's something you could actually try to answer with climate data. So according to CalAdapt, I want to plan my retirement party, which my accountant says I won't be able to afford to retire until 2070. But I want to have my retirement party at the San Luis Obispo Country Club, where I hope to retire in February 2070. So I want to know what weekend is predicted to have the least chance of rain for my retirement party. So this is, silly, right? But this, you can actually drill down and get the predicted precipitation and temperature for individual days. That's what these climate models have to chug out to get the profile of that bigger climate envelope. But obviously the data of the individual layer is not designed to be used at that resolution. So if I was uninformed, I might think, well, it looks like that last weekend of February 2070 is probably my best odds. Specifically that Sunday, there's only 2 out of the 10 GCMs are predicting rain, and even there it might just be mist or something. But you can do that. If you want to see how to drill down, if you click on that little link there, you can actually generate that plot yourself. So that's what not to do. Here are some general best practices for working with specifically the modeled climate data. I'm not talking about the observed stuff necessarily. Always look at multiple decades of data. You need to be aggregating in at least 20 to 30 years. 30 years is really what they recommend. Because these models that generate these climate data, that's what they're designed to do. They're designed to model climate, and that by definition is going to be that daily weather averaged or aggregated over 3 decades or more, right? So if your analysis is not looking at least 30 years, 20 maybe if you can, but at least 30 years of data, you're probably doing something wrong, right? You can still go down and look at individual days and say, was this day a frost day? Was this day a high precipitation day? But you need to then aggregate those daily metrics over decades. And that's the valid information that you can get from climate models. So that's important. That's probably the biggest mistake people make. Look at multiple models and emission scenarios, right? Certainly for the future, we don't know what it's going to look like. Global greenhouse gas emissions are a big wild card. But then there's also those models, there's between 4 and 32 models that you can look at. And there is some variability among the models. The variability is small compared to the variability in the uncertainty about the trajectory of carbon emissions. But still, you want to look at multiple models because they're our best guesses of what the future climate might look like. Another good thing to remember, look at the central tendency, right? So is precipitation going up? Is snowpack going down? What does that mean look like? But also look at the range of variability, both within models and across models, right? Because both of those are important. The variability is going to be super important if you're interested maybe in drought or extreme precipitation events, but it's also a representative of, maybe the amount of uncertainty between models, if you see that. So here we can see over time in this little graph here, this is average annual minimum temperature. We're seeing variability as time goes on, right? As well as the central tendency is also going up. Okay. So aggregate, right? Don't just look at one specific point in time, if you can. I mean, sometimes that is your study area and that's your study area. But you're going to get more reliable results if you say you look at a county than maybe this dot that happens to be in a microclimate. Average years together, or look at the dispersion across years. Look at multiple models. Take rolling averages. That's a good one to do. Spatially aggregate. Also, comparing things is generally helpful in climate science, whether you're looking at impact or something. The models by themselves are not that useful in general. Most of the time you want to say, how is that different than the past? Or how is this scenario, this future, and that future compared to each other? Or maybe different locations, right? So do comparisons. That's another general practice. A version of that is looking at what's called climate analogs. And this is where we run analyses that say, I'm sitting here in Berkeley, California today. In 50 years, it's going to be different. Where can I look today to see what Berkeley is going to look like 50 years from now? So like, what is the climate analog? I may have to go like, south, assuming it's going to get warmer here or drier here, right? So the climate analog is increasingly, I see that a lot in impact studies. Another question, which is not that intuitive, is like, if a lot of times we want to know, how is the past going to look different than the future? Or how's the future going to look different than the past? And you might immediately think, well, we have observed records from the past. So that's kind of the gold standard. So let me compare the future projections with the weather station data from the last 30 years. And that might be intuitive, but it's not really correct because those are representing really different things. The models are representing the climate envelope. The historical record represents one set of weather within a range of possible possibilities. So the historic record does not represent the climate envelope, and that's what the future represents. So what's generally recommended is you use the backward climate projections as the comparison to the future climate projections. And you might think, well, that's risky, but these models have been developed to accurately capture the climate envelope of the past, right? So if you're working with climate models, you have to, want to compare apples to apples. So that's generally what's recommended. So that's kind of the science side, but then there's also like, now we have to also think about how are we going to aggregate and make sense out of all of the possible climate futures, right? How are we going to store those? How are we going to turn them into probabilities and statements about proportions or rates? How are we going to compare them together? And then this comes down, yourself as a data scientist, you have to figure out how are you going to, what is your order of operations? What is your pipeline going to look like in terms of like computing the metrics you're interested in, aggregating across time, across space, doing comparisons and so forth. I'm not providing an answer here, but just kind of highlighting that that's an important question. So you might be interested in something like heat spells, right? So multiple days of high heat, basically what that is. And to answer that question, it's not difficult, it's really easy to get daily maximum temperature for as many years as you want, for as many GCMs as you want, for different time periods, for different emission scenarios. But then you've got like all of this data, right? For one county, you have 328 values for each pixel in that county, right? So your analysis is probably going to say, is this a hot day, right? So you're going to have to do something, write a function that returns, was this over a threshold? You're probably going to have to like look for consecutive heat days. And then, you're going to want to tally those up some way, possibly count the number of heat spells for GCP, for RCP, for the entire county. I would throw this little table up as a general suggestion for the sequence of operations, working with these kinds of questions. So first of all, filtering by space, like what area you're interested in, you can do that when you build your API requests, right? So that's usually early on. Likewise, your time range, build that into your API request. Sometimes you're not interested in the whole year. You just want to know the growing season or the cold season, or when this bug is going to be a problem, when this animal is vulnerable to heat or something. So you may do filtering within the year, right? That's probably what you're going to do next, right? And you can use the filter function for that. Then you're probably going to look at time slices, right? You're interested in maybe annual or the water year or the agricultural season, right? So you're going to want to group your data into time slices, And then I should have put it here, but you also want to group your data by the GCM and the RCPs, right? So that's another grouping. Then for each one of those groups, then you can start to compute your daily metrics. If you are doing something like looking for consecutive events, then you need to tabulate the runs. So for example, where do we see like 3 or more consecutive days of big precipitation, right? For flooding questions. In the cookbook, there's an example of how to do that. And then you start aggregating, right? So first you're grouping, now you're aggregating. You're gonna aggregate by your time slices, by your GCMs, by your scenarios. And then at the end of the day, come back and make some kind of comparison. So that's kind of like a generic sequence that you might use. Okay. All right. Fortunately, all of this is pretty easy to do in R. Well, it may not be easy, but it's once you know once you have an example, it's not a lot of code a lot of times to do these kinds of piped analyses. So generically, this is called data wrangling. I suspect most of you have played with this. R has got some really good packages that are for doing all kinds of spatial and tabular manipulations. I'm a big fan of cheat sheets. So these are my favorite go-to packages for data wrangling. We're not going to talk about those today, but we'll see examples of those. If you've used dplyr before, you'll probably recognize these functions. These are good for tabular data wrangling. And again, generic piece of advice would be, if you're like, well, how do I start, right? Think about what is the function that you're going to use for an analysis or for visualization, and then kind of work backwards. You know what you get out of the API, you know where you need to get to, and then think about what is the sequence to apply these together. Okay, I'll pause there. For any questions? We'll see more of this. Hopefully this will make more sense in Notebook. So let's go back to our studio, and I need to resume my RStudio Cloud project, and then open up notebook number 2, where we're going to look at some of this, some examples of data wrangling. I don't think we're going to complete it because I do want to at least show you working with rasters. So we'll spend maybe 10 to 15 minutes on this notebook number 2. Okay, so click on notebook number 2. I'm going to clear my console, and I'm going to clear my environment, get rid of all the variables already in memory. And we are now in notebook number 2. So you hopefully have RStudio open and notebook number 2 open. Find dash wrangle. Okay, code chunk number 1. So go down to code chunk number 1, Control-Shift-Enter to run all of those lines, reloading the libraries. This might look familiar. Here we are actually going to get data from one of those preset areas of interest. So code chunk number 2 shows you the preset area interest layers. You can do that. Code chunk number 3, go ahead and run that. Come down there. This is basically showing us the valid values for specifying one of the counties in the county layer. We can either throw it a FIPS code or we can throw it an ID value. I'm going to skip code chunk number 4. We talked about this already. Suffice to say, the FIPS code for Kings County is 06031. So code chunk number 5, go ahead and run code chunk number 5. And we are creating an API request object for Kings County, passing the ID value as a string. And the rest of it should look pretty familiar. Because this is a county, it's a polygon layer, you might notice the API request object includes the last thing there, the last function on that chain is specifying a spatial aggregation function. So we're basically saying, give us the maximum, because Kings County covers more than one cell, covers a bunch of them. So we're telling it to take the maximum. Okay, keep going. So code chunk number 6, go ahead and run that. We are plotting our API request object. We are asking it to overlay the grid of climate, the climate data grid, so we can get a ballpark idea of how many climate grid cells, 6 kilometer cells, cover this grid. Code chunk number 7 is actually going to grab some data. And again, you can change quiet equals to false if you want to see a little progress bar, but it usually just takes a few seconds. And we get back climate data. So this is now aggregated by, it's been aggregated for us. You can see the first column of the table that we get back is that FIPS code. So if we had another attribute table with other information for the county, such as demographic data, we could do a dply or join to join those back up. Okay, but what we're trying to do here is we're working towards a plot of some sort. So code chunk number 8 is doing a couple different things. This is just straight up data wrangling, data frame wrangling. We are adding that Fahrenheit column again, so that's what that mutate function is doing. Select, we're specifying just a few of the columns to get back. So we're kind of like getting rid of columns that we're not going to need. Pivot wider is a reshaping function that's from the tidyr package. And we're basically, previously we had RCP 8.5 and RCP 4.5 all in one column. And now that's basically splitting them out into 2 columns so that we can subtract them or compare them. Okay, and then code chunk number 9 is throwing up a plot. And so basically what this plot is showing, it's the difference between 8.5 and 4.5, right? So that's what the Y value represents. It's the difference between those emission scenarios. So basically it's showing that as time goes on, the divergence between the high emission scenario and the medium emission scenario is just getting bigger and bigger, right? So that's why they're always telling us we really need to get our global carbon emissions, greenhouse gas emissions under control, because the longer it goes on, the more and more we see a big difference. Okay, so that's what that does. Next, part 2 of our notebook, we're going to play with some of those functions to search the data catalog. So code chunk number 10 is commented out, but I'm not going to run it. You're welcome to run it. It's basically going to throw up the catalog of raster data in a viewer pane. And challenge 1 is asking you how many data sets there are. So we'll just do that together as a group. You can simply, it's a data frame, right? So you can say CA catalog _ RS and then pipe that into, say, nrow to return the number of rows in a data frame. And you can see that's 935 raster layers. I should say that many of the raster layers in the CalAdapt API are not necessarily going to be useful to you because many of them are populating the visualizations on the website. So the CalAdapt website, which is probably 98% of people work with CalAdapt data, is being powered by their API. So a lot of those are real specific to the charts on the website. Okay, let's keep going. So chunk number 12, go down to code chunk number 12 and run that. And you can basically see here we have a slug. So we're passing it name of a slug for one of those raster layers. And it's showing us the properties of that. So this specific one, it's a 32 ensemble model of snow water equivalent. Yeah, this one is probably, my guess would be, they made this for one of their website tools. Okay, but that gives you an example of searching the catalog. Okay, any questions? All right, let's see what more we should do here. Okay, we'll do the next section and we'll stop. Okay, so the next section starts on code chunk 15. And basically what we're getting here is going to be 20 years worth of daily maximum data, right? So the location here, it's a point location, obviously. And it's one of the research stations where they do a lot of citrus research. So you might wonder, well, in 50 years from now, are they going to be able to grow orange trees at this field station outside Visalia? So let's take a look at temperature predictions for this location. So code chunk number 15 on setting up the API request object. You can plot it if you want in code chunk number 16, see where this place is. Code chunk number 17 is actually going to grab the data and we can see what it looks like. It looks pretty familiar. We're getting, so this is 58,000 rows, right? Again, because we're getting daily temperature values, so it's a lot more rows than the other examples. Code chunk number 18, go ahead and run code chunk number 18. And basically what's going on here is we're adding that Fahrenheit column, but we're adding two other columns. We're adding a column for the month and we're adding a column for the year, right? So we have the date, because this is daily data, but a lot of times you want to slice daily data up by month or year or growing season or something like that. And the step to do that, you add the column. So that's what code chunk number 18 is doing. And you can see in the output, the new columns for the month and the year. Those are using functions from Lubridate, which is a great little package for working with dates. Code chunk number 19 is basically going to create a little box plot using ggplot and using a facet grid function to tell it to separate the box plots for RCP 4.5 and RCP 8.5, those two emission scenarios, and then to create a separate box plot for each of the months. Okay, I think we're going to stop there just because I don't want to, I want to look at the last notebook and slides on raster data. But if you wanted to keep going, you can see what else is here in this notebook is basically each one of those days we're looking at, is it over a certain threshold, right? So extreme heat is generally defined as is the maximum temperature above a threshold. Sometimes that threshold may be like based on the biology of, say, what is the maximum temperature an orange tree can tolerate in July or something like that, right? So some other times it's based on what is the 98th percentile of high temperatures for the last 30 years, right? So how the threshold is determined varies based on the question and the use case, but usually that's how extreme heat day is defined. So that's what the rest of this notebook is doing, and then we're just simply counting up the number of heat days. We're not in this notebook. We're not like finding the runs or the spells of heat days. But again, that's in the cookbook. Okay, I'll pause for a second here, and then we'll go back to the slides. Any questions? Okay. If this is a lot of overload, feel free to just kind of kick back and listen, and this, the slides and the stuff will all be there. Okay, so I'm going to blow through part 3 and go down to part 4, which is working with rasters, right? Because that's another format. It's got some advantages. Okay, so I'm showing back the slides now for working with raster data. You might wonder, well, hey, tables are intuitive to work with. Why would I want to go to rasters? Well, the climate data are inherently rasters, right? So you're getting the source data when you're working with the rasters. Rasters can cover large areas. So that's, many people are interested in large areas for your research. whether that's many locations or just one big area, like say, the southern part of our state. That's pretty big. Nice thing about rasters though, once you download them through the API, they're there on your hard drive, and you can use them as many times as you need. You don't have to keep downloading more data, right? Which is, so that can be an advantage. There's a lot of really well-developed tools and packages and other platforms for working with raster data and algorithms, like finding isoclines and all of the resampling your pixel sizes and projections and spatial extractions and joins. I mean, all this stuff is out of the box. We're going to be working with the STARS package here, but in general, whether you're working in R or Python or GIS software, there's a lot of functionality that's been built out for working with raster data. There are some challenges to working with raster data. They tend to be large, right? You've just seen working with daily data, that quickly adds up the amount of data. So you can have large file size. You can also have like hundreds of, depending on how your climate data is packaged into raster, you could wind up with lots, dozens or hundreds of raster files. So you just have to kind of like manage them, give them intelligent names, or create an index to help you find the ones you need. You still have this issue about like, how do we analyze multiple futures, right? So we just saw using a dplyr pipeline, how we can like group by and filter and summarize. So group-plyr has a pretty well developed to do that kind of staggered aggregation, computing metrics, summarizing. You have to replicate that with raster data if you're working with rasters. Another challenge is that the files are coming down as TIFFs. TIFFs is not designed for high dimensional spatiotemporal data. So there's some limitations with the format. On the next generation of climate data, they're going to use the ZAR format, which I'm not very familiar with, but I've heard it's kind of like cloud optimized GeoTIFFs, where time is a first-class citizen. So that should get easier in the future. But for right now, we're stuck with TIFFs. And then like any kind of raster, any kind of spatial data, you've got to deal with your regular spatial manipulations, such as like projections and getting everything lined up so you can swamp it. Oh, cool, Alex. All right, thank you, Alex. This is our expert. I should say that some people might be wondering about what's new for CalAdapt. Go to the website if you're interested, but basically the next generation of climate data is being prepared, and the next generation of CalAdapt API, it's not really going to be an API, it's going to be more like Earth Engine. So it's going to be an online analytics environment using Jupyter Hub, I think, to work with the next generation of data, which is going to be like hourly and an even smaller spatial scale. So they're moving processing into the cloud, which makes a lot of sense. Okay, but coming back to the here and now, so to get the rasters for the CalAdapt, you can go to the website. There's a data download tool. You can go to the FTP server. This Python package I was telling you about is also equipped for that, and there's a link to it here, and as well as a toolbox. My colleague Shane Fryer has taught a couple workshops on working with Jupyter notebooks, which included examples from this CalAdapt Pi package. It's not exclusively about those, but those are on YouTube. And I can put you in touch with them if anyone wants to use this. Okay, let's talk about getting rasters through R. So generally, the design strategy is that same API request object that we've been building. You can also use it to fetch rasters. You just feed it into a different function, specifically the function ca_getRast_stars. What that function does, it gets the rasters from the API. They're clipped to your study area. They're clipped to your temporal range, and it saves them to disk as TIFF files. General TIFF files, you can open them in remote sensing software or anywhere. But in addition to those TIFF files, this function also will create it's called a little sidecar file, which stores the metadata. Because the problem with TIFF files is that TIFF files can definitely have multiple bands, and you can give those bands names, but that's kind of it. It's not necessarily going to tell you what is the GCM for that layer, what is the RCP, what are the dates of each one. I mean, unless you encode those into the layer names in some kind of way. That's what these sidecar files are created for. And they're just RDS files, so you can open it, it's just a list object. It's not XML, unfortunately, I should have done that. But then once you've done that, you've got now a folder full of TIFFs, and then there's another function that we'll look at in a second that will bring those TIFFs into R as a stars object. So stars is a package. You might be familiar with the raster package or the Terra package. Those are for more like traditional remote sensing, three-dimensional data. The stars is kind of like that, but it's equipped for higher dimensional data, which is what we need here because we have a lot of GCMs. We don't just have X, Y, and time, right? So we have X, Y, and time, plus your climate variable, plus your GCM, your model parameters, or maybe it's a slug. Anyway, it's higher dimensional. So we're going with the stars package. And then the stars package, like raster or Terra, it's got a lot of built-in methods for filtering, spatial filtering, filtering for along the dimensions, say, for example, by date. You can extract, you can do spatial selections, your standard raster algebra. If you want to do pixel-wise summaries, so like drill down to every XY location and generate summaries, can do that. Your standard spatial manipulations like projections and resampling, all the normal stuff. The CalAdapt package does have some convenience functions that help you do these gymnastics with your raster data. There's a function that will create an index. So let's say you download and now you have 144 TIFF files representing different things. There's a function that will create a data frame, and for each one of those, each row represents one of those TIFF files, but it also tells you, the file name, what is the GCP, what is the climate variable, and so on and so forth, right? So you can use that kind of as a loop to do your data munging. There's another function that will take a list of rasters and put them into a 6-dimensional array, where those higher dimensions, again, represent the model parameters. And then there's another function that will take, if you're working with large geoms, that'll mosaic them. So here's the generic workflow for working with raster data with this R package. You create your API request, you feed it into that function. That function will communicate with the CalAdapt server, and then it'll take those TIFFs and dump them in a folder with the little sidecar files. And then it stops, right? It returns the file names, but it doesn't do anything else. But you can feed the result of that into another function, the CA stars read function, and that reads them into the R environment as stars objects, which are kind of like rasters. If it's a whole bunch of them, you can make it a proxy stars object. So that's where it's more like pointers to the TIFF files. It doesn't actually load them into memory. And then you're kind of on your own. You can use the stars methods to do your wrangling and analysis, or these convenience functions I was talking about, if that's helpful. There's 3 vignettes on the website for the R package that kind of explain some of the more complicated workflows in working with these stars objects. Okay. All right, notebook time. So let's go back to RStudio. And in the last 15 minutes or so, we will chug through and look at some of the working with stars objects. Okay. I'll pause for a minute as people fire up RStudio and open up notebook number 4. So fire up RStudio and go to notebook number 4. I'm going to close my other notebooks. I didn't say it explicitly, but after you've run a notebook, click the save button, and then you'll notice in your file pane in RStudio that an HTML file magically appears. Right? So every time you save a notebook, all of the code that you've run will be encoded in that HTML file. And then at the end of today, if you want to download those HTML files to your computer, assuming you're using RStudio Cloud, you can just select them, and then there's a download button under, it's called export. And so if you want to get your HTML files to your local computer for posterity, you can do that within RStudio Cloud using the export button on the file pane. Okay, so, but let me go to notebook number 4. All right, and again, I'm going to sweep my console and sweep my, if you are using RStudio Cloud, I would recommend that you clear out your environment. So go to the environment pane and click the little broom button. And the reason I say that is because a free RStudio Cloud account only gives you like 1 gig of RAM, I believe, which you might run out of memory. So start this notebook with a fresh slate. Be my suggestion. Okay, any questions? Okay, let's go to notebook number 4, rasters. Go to code chunk number 1, Control-Shift-Enter. This is all the same stuff. We're loading up some packages and specifying our preferences for function conflicts. And basically what we're going to do in this little notebook is we're going to download some rasters for the Sierra Nevada ecoregion, which was one of the 7 or so regions that were studied as a unit in the 4th climate change assessment. It's pretty big. So go ahead and run code chunk number 2, and you should be able to diagnose what we're getting here, right? So we're getting that big region. It's one of the preset areas of interest, so we're not passing it a polygon. We're asking for Livni data, so that should tell you this is observed interpolated data. Okay, does somebody have a different notebook? Oh, Naomi. Okay, so Naomi, you probably have, my guess would be you cloned the RStudio Cloud project like a couple of days ago. So what you could do is just grab it. You know what you should do? You know what you can do is if you go to the, okay, that's fine. If you do want to grab it, if you go to the menu for our workshop and click on the notebook for rasters, there's actually a little button. It opens it up as a rendered HTML file. But if you click on the code button, you can download that R&D file, and then you can like copy paste it to your RStudio Cloud environment. So that's what you do. Or just follow along. We're almost done. Okay, so that's what code chunk number 2 is doing, is creating an API request object for yearly precipitation from the Livni data set, which is observed and then interpolated over space. Okay, and you can see the little leaflet map that opened up. It's a pretty big area, right? So this is it's a good chunk of the Sierra Nevadas. Okay, code chunk number 3 is where we're going to download this data as TIFFs. So go ahead and run code chunk number 3, and you can see there that we are specifying an output directory, right? So it's a data subdirectory of the notebook folder, which you see it there. And we're telling it to throw the rasters into that directory. Also, you may have seen it says overwrite equals false. That means if we've already downloaded, that file is already there. It's not going to download it the second time. So that's generally good practice, is save your rasters in a same location, and then you don't have to download them multiple times. And if you click in the data folder in your RStudio files pane, you can actually see there's a TIFF file in there. And then above it, you can see that sidecar file I was talking about. You don't need to open it. So you should, probably that went really quick because actually it didn't download anything because it was already there. Right? But if it wasn't there, it would have downloaded it. And this is not a ginormous TIFF because it's yearly as opposed to daily. And I think we're only grabbing, and because it's Livni data, we're only grabbing, it's just one set of values. It's not like 4 GCMs times 2 RCPs, right? It's a single value. But it'll be good for our purposes today. So code chunk number 4, this is where we've downloaded the data into a TIFF file. Now we're going to bring that into the R environment using this CA stars read function. And what we're feeding it is going to be the file names that we generated before, right? So it's loading them in, and it's what that CA stars read function returns is a list. It's a list object, and each element of that list is going to be one of those stars objects. Okay, so if you look at code chunk number 4, we can see there's only one element of this list because all of the years were squished into a single TIFF where the different layers of that TIFF file represent different years. So there's only one TIFF. And if row 79 or line 79, this is the actual stars object, right? So if you haven't worked with stars object before, I'm sure you probably worked with arrays, like your traditional 2-dimensional array. This is basically that, but then there's extra dimensions, right? So you can have, here we just have X, Y, and then a time dimension, which is year, but you can have many, many other dimensions. We talked about before those 6-dimensional arrays that you can put together. And we can see there's also spatial information. So we can see that there's a coordinate system here, WGS84, and so on and so forth. Code chunk number 5, go ahead and run code chunk number 5. And here we're plotting, right? So this is a array of, it tells us we had 41 layers. So we don't want to print out 41 plots. So if you look at that code chunk number 5, you can see we're just getting 4 of the 41 layers. That's what that slice function does. So that's an example where we're using slice. That's a dplyr function, right? Which we use to, in a tibble, you would use it to select rows based on their index number. Here, we're using the same idea. We're applying it to a stars object. And in addition to telling it what indices that we want, the along equals year, that's telling it, go to the year dimension of this 3-dimensional array and give us back, the first 10th, 30th, and 40th element along that dimension. So that's basically what's going on there. Okay, let's keep going. If you're not following every nook and cranny, that's okay. Code chunk number 6 is simply going to show us specifically what are the units, right? Because if you look at that plot, the numbers are going from like 0 to 12. And this is like precipitation data. So you might be scratching your head like, is that feet? Like, what is this? So it's not entirely clear, but the units are millimeters. More specifically, these are the millimeters per day on average. So this is not like millimeters per year. There's more than 12 millimeters of rainfall in the Sierras. But you multiply that times 365, and you'll get an estimate of the total rainfall for 1 year. Okay, so let's keep going here. We'll do just a few more, and then we'll wind down. Code chunk number 7 is basically getting that stars object, right? 41 values, and we're using the filter function, which again has been adapted from dplyr. And inside the filter function, we're putting in a couple conditional expressions with the name of one of the dimensions, year, saying only give us back those layers from the year dimension where it's greater than 1990 or less than 2000. So now we can see in the results where we only have 10 layers instead of 40 layers. We have the 1990s. Okay, code chunk number 8. Go ahead and run that. And this is illustrating how you can actually get the values of an individual dimension, right? So year dimension, the values are going to be integers, the years. The X range, X is simply another dimension of our stars object. And you can see there, that's going to be the longitude coordinates, because X is a spatial dimension. X and Y are spatial dimensions. So you might wonder, why would we do that? But go to code chunk number 9. Code chunk number 9 is illustrating an alternative way of subsetting your stars object, right? Where before we used slice or filter, and those work, but those are dplyr methods. But stars objects also support square bracket notations for subsetting by any of the dimensions. There's only one, so this should look familiar if you're familiar with the stars with the square bracket notation. One thing to note though is that there's an extra comma at the beginning, right? So there's 3 dimensions here, so we need at least 3 slots for the X, the Y, and the year, as you would expect with like a regular kind of array. But in addition to that, there's another slot at the beginning, which we're going to use for spatial selections here in a second. But you can see here, the last slot inside the square brackets is a which function. And then we have inside there, because with square brackets, it wants indices. Unlike base R, when you're using square bracket notation to subset a stars object, it wants indices. You can't give it logical vectors like true, false values. So which just turns those into indices. Okay, let's keep going. Last 5 minutes. So code chunk number 10, go ahead and run that. And basically what we're simply getting a simple feature polygon layer, because we're prepping to do a spatial selection. So you might recognize the boundary of Yosemite National Park. That's what we're downloading and bringing into R using the stread function from the SF package. And now go down to code chunk number 11. Here again, we're seeing that square bracket notation to subset this multidimensional stars raster. And if you look at the results, the X and Y dimension. So basically that first slot in the square brackets, we throw in this simple feature data frame that's in the same coordinate reference system, WGS84. And basically it's going to subset spatially. So now if we plot that, so go down to code chunk number 12, assuming code chunk number 11 worked, you can see that it did indeed subset that big raster that covered all of the Sierras to just the bit that covers Yosemite Park. So that's kind of cool. And it does masking, right, by default. So all of the cells outside of the park boundary are transparent because their values are NA. If you look at the scale bar there, we're still getting values like between 3 and 5. And again, that's because these pixel values represent the average daily precipitation. And we're picking just one of the years, right? So to make this plot, if you look at the code chunk number 12, we're using that slice function to just show one of the 40 layers, the first one in 1970. Code chunk number 13 is basically doing map algebra, really. So I'm tired of looking at the pixel values that are, the average daily temperature or daily precipitation in millimeters. That's not, I would rather see total precipitation for the whole year in inches. So code chunk number 13 is just taking that stars object that we just made and multiplying it by a couple numbers to convert the values, the numeric values of the pixels, to inches of yearly rainfall. Estimated, I should say, because we're it's just multiplying it by the number of days. And then code chunk number 14, we can plot that. Looks real similar before, but now the numbers are 45 to 75, right? Because that's about the number of inches of rainfall that Yosemite gets. But you can see, Yosemite is pretty mountainous. And it's definitely a lot drier on the eastern side of the hills up there. On the Nevada side, it's a lot drier over there because of the mountains. Okay, finally, we'll stop here. Code chunk number 15. This is pretty useful. A lot of times you want to do some sort of pixel-wise summary. This is a simple one. We're just simply taking the mean. It could be something more complicated where, like degree days or some other kind of pixel-wise summary. That's a little more. But basically, the function in the stars package to do pixel-wise, like kind of drill down in one of your locations, or doesn't have to be a location, as we'll see in a second. But this is real similar to the apply function, right? If you remember your base R and using the apply function in the arrays, you pass it the margin argument. Those are the indices of the dimensions that you want to keep. And then it's going to apply that function, in this case, the mean function, to all of the other arrays, kind of all the other dimensions collapse together. So here we're getting in code chunk number 15. Now we have just one layer left, and this is the average total precipitation per year clumped over all 40 years of data. So that's aggregating over time. And then code chunk number 16 is doing something similar. Go run code chunk number 16 and then code chunk number 17. That's basically, it's the same thing. If you look at the st apply function, the only thing that's different is that the margin argument, we're saying instead of, leave us the X and Y dimensions, in code chunk number 16, we're saying leave us the year dimension. So basically it's taking the park, and for the X and Y dimensions, it's averaging all of the pixels for each year. So what we get back is a one-dimensional array with one attribute. And then in code chunk 17, we're converting it to a data frame and then plotting it. So that's what that does. Okay, let me pause there. We're just about at time. We basically got through most of it. I think the take-home message, hopefully the take-home message is that R is really powerful. It's really, really powerful as a data science platform. It's not surprising that you can do so much with it relatively easily, including climate data. And getting the data into R is never easier, thanks to well-developed APIs and package. So hopefully this will be useful. I like playing with this. I'm still very much developing, certainly developing the documentation and tutorials. Love to get collaborators, free consultation if anybody wants to work with climate data in R. I've got office hours every week. I would love to do a hackathon someday because there's so much need for decision support tools involving climate data. We've barely tapped the need. It's easy to talk about temperature, but how's that going to affect the stuff we really care about in the future? A lot of need for that. So I'll pause there and I'll stop and take any questions.
Well, thank you so much, Andy, for this. This is going to be an incredible resource. I know I'm going to go back through the workshop materials because I'm working on some climate stuff myself right now. So I really appreciate it. And I want to thank everyone for joining us. We're right at noon. So I want to be aware of time. If anyone has to run, feel free to run, but we can hang out for a minute or two and answer any questions. I'm going to go ahead and stop the recording so you can feel free to ask all the questions you want.